Howdy, my name is Jared Wilson, and I'll be presenting over bistatic and multistatic radar imaging and signal processing. First, bistatic and multistatic radars. Bistatic radars are radars that only have a single transmit and receive antenna, and these antennas are separated by a sizable distance. And another important factor is these receiving antennas have a passive output, so they're very appealing for military application and low noise. And multistatic radars are a system comprised of multiple monostatic or bistatic radars that are all connected together. And then this system is normally able to get a better perspective on single targets by imaging from multiple locations. Here's a photo to see that better. So this actually has a single transmit antenna and then 3 receiving antennas. You can see that these are each connected to a node controller that sends it back to this master computer that does a final compiling of all these signals to make a single output. How do we actually get these images, and what signal processing has to go into them? The first signal processing is done by analog hardware. Normally, the received antenna or the receiver antenna is immediately passes the signal into a low noise amplifier, and then that runs through a bandpass filter and a mixer, and then from that it is finally output to an analog to digital converter, which samples that signal at least 2 times the output frequency to ensure that all the data is retained, and that is then passed into a signal processing computer, which starts with pulse compression that is done by modulating the transmit pulse and cross-correlating it to the received and transmitted signals. And then the signal is run through a clutter rejection filter that reduces the clutter echoes and enhances the target echoes. This is normally done through a fixed band filter with the center frequency intentionally placed to cut out spectrum clutter. And then finally, after the signal processing computer, it is sent to a more general processing computer that starts by ensuring that there is a signal here, and then thresholding that to help identify targets, and then estimating parameters such as velocity, range, and the respective errors for each one of those. And finally, taking all of that and outputting it to the user, so then it can be properly tracked visually and displayed to them. Research areas on the bistatic and multistatic radar. The University College London is working on a multistatic radar system that is able to accurately move the antennas without requiring calibration. This is incredibly useful because these multistatic systems require much more complicated reflectors, while most monostatic systems use trihedral corner reflectors. These multistatic systems require much larger objects like a large metal sphere or a cylinder that are quite challenging to accurately place and require recalibration every time that these antennae are moved. So having a system that can change its target sampling area is very appealing. And then for next generation weather radars, the National Severe Storms Laboratory is working to develop pulse compression waveforms that have a ultra low noise side lobe, which is helpful for extreme weather conditions due to just the lack of reflections that are coming back. And reducing these side lobe levels allows them to sample at a more accurate rate, and ensuring the incoming signal is not influenced by the side lobes from the transmitting signal. Future technology, direct sample receivers, which are helpful for 5G communication due to just their large bandwidths, and being able to capture a large section of the spectrum at a single time is very appealing. And then multistatic radar systems in the future traffic systems to work with self-driving cars by allowing these cars to see multiple car length in front of them due to like side reflectors mounted on the roads, and just communication between these systems to make a more homogenized driving. These are my sources, and thank you for listening to my presentation.